Actually, before you
Go ahead, Tony.
I was saying something bizarre is going on with Zoom for me today. If you look in the participants list, you can probably work out what it is. I was wondering if you were able to rename me in there.
I actually can promote you to host, and I believe you should be able to rename yourself.
I don't see. I can add a profile picture. That's it, though. Oh, okay. Thanks.
Okay. Good morning, good afternoon, good evening, depending where you are. Welcome to 7th UCF workshop. People still joining, but we'll get it rolling because we're short on time. This is our 7th workshop. This is our second fully virtual workshop. Due to COVID in everything, we figure out it will be easier to continue it in a virtual format. Even so, we'd love to have you again in Austin and hosted at ARM, but unfortunately not this year. We will kick off the day with a short introduction by myself. I'm Pavel Shamis from ARM, and my co-presenter is Gilad Shiner from NVIDIA. Before we starting the meeting, I have to show this disclosure slide, which essentially stating this is a public forum meeting. Whatever is discussed here, it's an open and publicly shared. Some of the housekeeping notes. First of all, to get up-to-date schedule, you can visit our GitHub page. We have a link on the slide in the same page we used to advertise a workshop. Here's also Zoom link. The same Zoom link we'll be using for all 3 days. We already shared with people that registered for the workshop. If you have some other friends and colleagues in organizations that want to join, feel free to share the link. The session chairs, myself, Pavel Shamis, Oscar Hernandez will be chairing sessions on the last day, and tomorrow is Matt Baker from Oak Ridge National Laboratory will be chairing the session. All our presentations are video recorded. When you joined the meeting, you click the button stating that you accept that it's recorded, so you gave us disclosure. We also will be posting all the video recordings and slides later online. Typically, it takes from a couple of weeks to a month to get us everything processed and uploaded to YouTube. Some of the etiquette notes. If you're not presenting, keep yourself muted. You can leave your video on. We kind of highly encourage, especially if you're a presenter. It's encouraged to leave your video on. It makes presentation much more engaging. We encourage people to ask questions and participate in discussions. There is few ways to do it. You can ask questions in Zoom chat, or towards the end of the presentation, or depending on presenter, you can unmute yourself, ask questions, and so on. We will leave some time towards the end of the presentation to ask questions. Again, you can raise hand in Zoom or mute yourself and ask it. We also have additional facilities available for us, like Zoom whiteboard, that people can use to have whiteboard discussions and so on. Not necessarily all meetings going to be, entire meeting is going to be a PowerPoint. Last year, some of the meetings we had just code discussions with the code and whiteboards. Any questions so far? If you present on the schedule, I will be asking before the meeting, before your presentation, to raise a hand and give me a signal so I know how to promote you a presenter to co-host and host. And once you co-host, you should be able to share your screen. This is our schedule for today. We have a variety of talks scheduled. The talks, not just about UCX, which is our flagship project. We have a variety of talks about RDMA and SmartNICs, MPI, and so on. For today, we have a talk about ByteCCL. We have talks about using UCX on AI clusters in Azure. We have talks about MPI integration with UCX. We have separate section dedicated to UCX bindings, which is Java, Go, and so on. And towards end of the day, we have talks about OpenSHME and database in cloud. We'll have breaks in the middle. I think overall schedule 2 breaks, each one of the breaks 30 minutes. So we do, if your presentation runs over, you have some buffers but if you'll see that overall time goes over 30 minutes and we're really late, we'll ask presenters to hurry up. This is scheduled for the rest of the days, and I will not spend much time here. I want to acknowledge some of the people. First of all, I want to acknowledge UCF board and organizing committee for helping us with organizing the conference. This is the first year we did official call for presentations with peer reviews, and it consumed a lot of resources and time from people. So I want to really thank organizing committee. In addition, I want to especially thank Oscar Hernandez, Ned Baker, and Kim Chan Song for helping with organizations. They tremendously help with managing website, issuing call for prayers, organizing calls, and reviewing presentations. I believe this is my slide, and Gilad, the floor is in yours.
Thanks, Pasha. And of course, many thanks to you for helping with all the organization and driving the sessions and so forth. So looking forward for great few days with great sessions and great discussions. Next slide, please, Pasha. So I'm not going to spend too much here. We have a short opening session. So first, the UCF Consortium was created to drive collaborations between companies, commercial companies, government labs, universities, individuals, to actually create communication frameworks and open standards to enhance supercomputer platforms, AI systems, data centers as a whole, and so forth. There are several projects that are being developed under the UCF Consortium, including UCX, which was actually the first project that started or operate underneath the umbrella of the UCF Consortium. For point-to-point communication, UCC project for enabling collective communications, kind of the sister or the brother of UCX. Some other projects to mention: Open Smart Network API, to build a standard API to access services, compute services that can be provided from different networking components, and Open HPCA, which is a benchmarking offer to create a benchmarking suite to be able to measure computing resources or computing performance from the network components or from the fabric. Definitely want to thank all of the board members that help to drive the mission of UCF, organization, sessions, presentations, and so forth throughout the year. Looking forward to continue with activities next year as well, and driving more capabilities into our projects. If you join us today, so you probably know what's the URL for the Ucf Consortium and how to contact the folks in that consortium. But if you forgot, you have that on the bottom of the page. Next slide, Pasha, please. So why did we start with it? Why did we start? Why doing UCX? Motivation was very simple. Wanted to provide a low weight, high performance communication framework that can support variety of data center applications, obviously looking on HPC and supercomputing and AI, which falls underneath the same part, but data analytics and storage and other elements, supporting all compute elements on one side. If those are accelerators or CPUs, x86, ARM power, you name it, and be able to move data in a very effective way from one side, one memory domain into another memory domain. So that's how things started. That was the motivation behind that. And today, UCX is probably the mostly used communication framework across HPC domains. If it's MPIs or AI frameworks or data analytic frameworks and so forth. We were very proud of that, very proud of the collaboration, the ability to support variety of networks, everything, almost everything that exists, and to build something that can be very portable and support all memory elements on all computing elements on both sides of the network. Next slide, Pasha, please. I think I have 2 more slides, so we'll go quickly on this one. There is growing amount of users, growing amount of HPC users, UCX users, growing amount of application utilizing UCX for different things. MPIs, obviously, or other frameworks, if it's PGAS or SHMEM. Charm++, which enables, for example, NAMD to work directly over UCX and through UCX to connect to the networking infrastructures. Rapids, Dusk, AI perspective, Spark, different kind of companies, frameworks, and so forth. You can see the list here. You can see a couple of diagrams. We see increase of usage, and actually sometimes we learn about usage of UCX after that's fairly established. We see UCX being used for new generation of file systems, just as one more example that we don't see on the slide. But it's growing. It enables different kind of workloads, which is the great benefit of UCX. And it has, I mentioned before, it actually become probably the de facto communication framework for point-to-point connectivities. Then next and last slide, Pasha, please. Thank you. So obviously there is a lot of content on UCX, on UCC, on HPCA, the benchmarking suite, and OpenSnappy. Mailing list, obviously join the mailing list. You can download the code, look on a different kind of presentation that we have on the website. We had a Birds of a Feather session at supercomputing where we presented a lot of the development in the different areas. We will try to point to that or see if we can put the video on the website, but there's also videos from previous conferences as well. If you think that there is missing pieces of information that can help to understand the development, usage model, and so forth, please don't hesitate to let us know. We want to make sure that everything is accessible, simple to understand, simple to integrate, and simple to use. So with that, back to you, Pasha. I believe we're on the 15 minutes for the opening session. Looking forward for the coming days. And again, thanking the speakers before they presented, by thanking the speakers to develop their content and their willingness to present in the next coming days.
So let me present the next speaker. And if you can raise a hand meanwhile, Peter, I think you're presenting, right? Let me promote. So Peter, you should be able to start, try to share now. And meanwhile, I will do introduction. We have one more raised hand. Habin, okay. And done. I will stop sharing for a second. Guys, you should be able to try to share your slides. And if you don't, please unmute and let me know. And meanwhile, I will do the introduction. So our next talk is about accelerating recommendation model training using Byte, CCL, and UCX. I believe the presentation will be done by Habin Lee. And we're starting to see the slides. Meanwhile, I will show some interesting statistics. We had over 100 people registered for this workshop. I believe this is our largest virtual event. Generally speaking, virtual event has been work out very well for us because attendance and number of people registered more than doubled. So I believe in the future, we will continue with this model. We'll be running some sort of hybrid workshop where we have virtual presence and presence. Can you guys speak up? Let me know if, because I can hear you, but I can see the slides.
Sure. Can you guys hear me?
Yes, we can.
Hey, Habin. Yes, we can.
All right, cool.
So I will mute myself and floor is yours. Thank you.
All right, thanks. So my name is Haibin. I'm from ByteDance. I'm a research scientist working on machine learning systems. So in today's talk, actually, Mikhail is also joining me. It's a collaboration between ByteDance and media on the ByteCCL project. And Mikhail will also cover part of the talk regarding how UCX and some components in ByteCCL are integrated together. Mikhail, do you want to briefly introduce yourself?
Yes, I'm a software engineer from NVIDIA, and I was helping Haibin to introduce UCX transport in BytePS. And we achieved some quite good results, and Haibin will talk about that right now.
Mm-hmm. Okay.
So guys, sorry for interrupting, but at least for me, Habin, you a bit breaking up. So there might be a connection issue. You may try to disable video and see if it, fix the sound.
Okay.
Pasha, I can hear Haibin quite well, but I hear you interrupting.
Really? Okay. So
Yes.
then it's maybe me. Okay, then you're fine. Then sorry.
Okay. So I guess I'll continue. Yeah. So in today's talk, I will briefly talk about the recommendation model training workload and give some overview of what 5CCL offers and its architecture, and then Mikhail will talk about the integration part with UCX, and finally I'll talk about some optimizations we did in BiCCL, and as well as some of the performance result we have, some preliminary performance result we have. Okay, so let's start with the recommendation model training. So for recommendation models, it's actually quite important in the industry. So for many important or successful search engine or social media applications, it plays a very important role. For instance, if you visit Amazon.com and you type some items you want to buy in the search bar, it actually goes through the recommendation system backend, and it promotes some of the top ranked items to you in a very short page, right? So it retrieves from a very large number of items and present only a few numbers of them to you. So it selects very high ranked items. So let me see if I can turn on the laser point. Okay, so in general, the system will collect the all the logs regarding user actions in the backend, and so it knows, for each query which items the user clicked in the history, so that it knows the relevance of the items in the query. So this kind of data is stored in the backend, so that some of the machine learning models can use this data to learn some models. And at serving time, whenever it comes a query, it goes through 2 stages. So the first stage is the retrieval stage, where we select only a few hundred or 1,000 items from a large pool of, maybe 1 billion or 1 million items. So usually the retrieval phase is kind of light, and it does not involve a lot of computation because it deals with a very large number of items. And then with a small number of candidates, for instance, a few hundred, it goes through the ranking phase, where in this phase the model can be more complicated. It can involve more compute with some kind of neural network, and the output of this phase would be a few dozen of items that will actually show up in the page that users see. So in today's talk, I'm actually referring to most models in the ranking phase, where the model is slightly more complicated. It can involve some of the neural networks that people train, and involves large models that can be terabytes of memory involved, and also it's communication heavy. So that's kind of the context I want to provide. And so this is one page that talks about what the model is like, so that you can have some context on what the model actually do. So the model will have 2 types of inputs. So first of all, some dense features, including some age information or number of views if you're watching a movie. So most of these values are continuous, some floating point numbers. And the other important part is the sparse features. So usually, for instance, if you're watching movies or reading books, there are many different books you can read. So it involves a class of maybe 1,000 or 1 million books, and we cannot really represent them with floating point numbers. Usually we assign some in class index to different types of books from 0 to maybe a 1. But we cannot really represent the difference between different books using this number, but rather we would have to have some kind of representation using a vector to represent them in the high dimensional space. So this is what we call the embedding table lookup. So for each book, we have an index representing its index, and we have a vector that represents this book in high dimensional space. And this is what we call embedding, and this is used to as the input to some neural network layers that we map this input to some nonlinear functions, and later we can learn some loss function based on it. So this is roughly what the model is like. So in terms of the workflow characteristic, very important part is that this sparse feature is related to the very large embedding lookup table, where we have several million items, and for each item there's a vector representing that. So if we have a 1 billion items, then the embedding table would be really huge. And if each item has 1,000 floating points represented, then the number of parameters in this lookup table would be 1 billion. So that corresponds to several gigabytes of memory. So this basically brings some challenge in training this model, because this embedding table is huge. And in comparison, the neural network layers are relatively small. It usually only consumes about less than 100 megabytes of memory. So this part is kind of small. And most of the communication happens related to the embedding layer. That's the kind of the characteristics of this workload. Okay, so so how do we actually train this model? So this is one diagram that shows an example of how we train this model. So in this figure, I'm giving an synchronous training as an example, but in practice, there are many ways to do it. And this is one figure I took from HugeCTR, which is a recommendation model training system from NVIDIA. And in this figure, we can see that, so in terms of the parameters, there are two types, the neural network, which is usually very small, and the embedding part, which is huge. So the neural network is replicated across different workers, and the embedding is so huge so that it has to be sharded across the workers. And so this is about the replacement. For the communication part is usually the all-to-all communication primitive, which is used to exchange the sharded embedding lookup result from different devices, so that for each data batch, it contains the sparse feature that is related to different shards in the embedding layer, and the result can be then gathered, use all-to-all, so that it can reform the embedding for this data batch completely, and then feed into the neural network. Okay, so this is like one example of how the recommendation model can be trained, and the primitives involved here is the all-to-all primitive, as well as the all-reduce primitive for the neural network layer. But the neural network layer is kind of small, and the all-reduce usually does not take too much time. But in practice, people have found many other ways to design the system. For instance, here are some design choices of how the system can be trained. For instance, there are some choices of choosing whether we do synchronous training or asynchronous training, where in synchronous training for each training step, there's synchronization involved to sync the states of different workers. So this is usually better for model convergence, but in terms of system performance, it's usually lower because there's some synchronization involved in each step. So that's one difference. And in terms of the communication primitives, it's very different because for asynchronous training, each worker proceeds at its own pace. So the primitives involved would be some point-to-point operations such as push-pull, similar to send receive, or gather and scatter. For instance, you can use the gather to gather all the embedding for one data batch, where the embedding are lives in different workers, different worker shards. In comparison, the synchronous training would only use all-to-all because everyone proceed at the same pace. So that's one difference. The other is the embedding placement and the choice of devices. For instance, the huge CTR system is designed around GPUs, and it has very high memory bandwidth and also compute capability, but it also has a very low memory capacity if you compare it to CPU or SSD. So there are different choices on how we place the embedding on these different devices. And for instance, if we design a system where the embedding is placed on the CPU and the neural network is on the GPU, that means that for the all-to-all or gather scatter operation, the source and destination devices may not be on the same type, right? So there are some optimizations we need to do if there are on different types, depending on the topology. So that's another consideration. Okay. So that's so previously these are about the workload we care about, and BiCCL is one communication library we designed for this workload, and it's built on top of BiPS, which is already open source. And BiPS is mostly designed around the all-reduce operation to support computer vision and natural language processing applications. And BiCCL is kind of an extension to it with more communication primitives like gather, scatter, and all-to-all, so that it can be extended to support more use cases. One of the important ones we're working on right now is for the recommendation models. So apart from these 2 points, it also supports both synchronous training and asynchronous training. It's integrated with the multiple machine learning frameworks, similar to Horobot, for the popular ones such as TensorFlow and PyTorch. It also is supporting different hardwares. It supports both CPU and GPU for now. For instance, for the all-to-all variants, we have all-to-all inputs from the CPU device directly to the remote CPU device, or from CPU to GPU and GPU to GPU and vice versa. So there are different combinations that we support and optimize based on the hardware instance types we have. Okay, and so here's the slides about the architecture. So BiCCL is the communication layer between the machine learning application as well as the hardware. So under the hood, there's another library called PSLite, which BiCCL relies on to do the actual communication. So if we look at the BiCCL layer, it has the framework integration code, for instance, using the TensorFlow API to do some memory allocation and so on. It has some logics about different collective algorithms, such as auto and all reduce, and also some scheduling part related to how we optimize the communication if there are multiple tensors to do all reduce by combining the information from the computation graph from TensorFlow. So it also provides Python APIs for these communication primitives, similar to Hardbot. Under the hood, there's the PS Lite layer, where it provides the C++ interface for control plane and data plane. For the data plane, it's mostly the push-pull API, which is kind of similar to send and receive, but not entirely the same. And then for the transport layers, we have different backends. It has, for instance, 0 and Q to support TCP. We have also the RDMA event to support CPU RDMA memory, and as well as IPC, as well as Fabric band, which runs on AWS EFA, and the new band is called UCX band, which Mikhail works on, help contributed a lot to enable PS Lite to support GPU memory, as well as these different transports. Okay, I guess Mikhail, you can take over and talk about the UCX part.
Okay. So initially we were thinking that UCX would be a good fit for PS Lite because PS Lite has quite good abstraction for transport layer, and it is enough to implement a certain abstract class to enable new transport in it. And the main motivation for using UCX in PS Lite for us was to enable GPU memory support, multi-rail support, and I think DC is also important. DC is a dynamically connected transport, which is highly scalable, RDMA capable transport, unlike RC, which has certain limits on scale. And with multi-rail, I mean that with UCX, it's possible to use all the network devices which exist on the system for message transferring. And by enabling UCX in PS Lite, we would enable all these features. So that's why we tried to do that. And besides that, UCX exposes many more features, but those are the most important ones needed for this use case. Haibin, can you please move to the next slide? Okay, this is a diagram of UCX layers, which shows what we have here. We have support for various networks. We have support for host memory, for GPU memory, and we have different high-level protocols for different intended for different use cases. And with PS Lite, we used Tech API, which is available as a part of UCP. And we can move to the next slide, please.
Oh, it's stuck. Okay.
Yes. So we used Tech API because at that time it was the most mature API which supported all the mentioned features. And we have a bit more details on the next slide, but in a nutshell, we were using sending function for send messages, and the network polling was implemented based on probing messages sent on the receive. And we had to do some optimizations, and we have some schemes on the next slide. So also worth to mention that it's multi-threaded framework, so we had to use multi-thread support in UCX. And initially we used a model where we used common UCP worker for all the threads, but then we noticed that this is a source of some performance overhead, and we had to do some optimizations. I will talk about it a bit later, but now the common scheme is that for implementing transport layer in PS Lite, it is enough to implement just a few communication methods in the abstract class. And for sending message, it is required to send two messages actually. One is metadata describing the payload which comes right after it. And so it's on the sender side, it's just implemented by using two-text sends. And on the receiver side, we have a polling thread which is constantly probing the network for specific tag, waiting for the meta message describing the payload. And once we notice that we receive some meta message, we take all the details from it, like length of this message, its ID, etc. These details are needed to allocate the proper receive memory buffer to get the message into. It's not really a real memory allocation because we have a specific memory pool on the receiver side, but we have to know certain details to get the proper buffer from this memory pool. And then we call take receive function, which gets the payload itself. And once we get the message, everything is done in this polling thread. Well, once we get the message, we push this data to the receive thread using thread safe queue. And then the message comes to the upper layer, to the application. And that's the scheme. And that was initial implementation, and we had to do some performance optimizations afterwards. At first, we tried to optimize performance for relatively small messages, and we implemented so-called short protocol, where we bundled metadata together with payload. We just used UCP IOV type, and we started sending just one message instead of two. The drawback of this protocol is that it doesn't support GPU memory yet because it uses IOV data type. But it noticeably improved performance for small message sizes like 100 of bytes. When I say small message sizes, I mean 100 of bytes or maybe up to kilobyte. Also, as I mentioned before, we noticed that using a common worker for all the threads introduced quite notable performance overheads. So we divided. We started using different workers for sending and receiving threads. That helped us to avoid logs. Many logs on the data path, and also have been added lockless thread safe queue to the byte PS, and that also helped to remove some logs and improve overall performance. And another important optimization was to implement separate UCX context per GPU device on the system. And the motivation for this optimization is that currently UCX during startup selects the most optimal devices and protocols based on internal analytics, which UCX will use for communication, but it doesn't take into account memory type of the data which is being transferred. Currently, it's not taken into account by UCX, and due to this fact, UCX, when during initialization, selects a certain HCA or network adapter for communication. And if we have a bunch of them, as well as a bunch of different GPUs, like for instance, we have on DJX systems, it may be quite inefficient if we trying to send some memory, some buffer residing on the GPU memory, which is located quite far from the network device which was selected by UCX. So we did it this way, that we created different UCX context per each GPU device, telling UCX which GPU is currently enabled before creating every context. So so that UCX would select the proper HCA or NIC for that. And then in BytePS, then we made the mapping in BytePS and in UCX transport, that once we get some GPU memory to transfer, we also get a device number which this memory belongs to, and based on this information, we select a proper UCX context to use for the transfer. And this really helped to improve the performance. And it may sound like quite a complicated scheme, but currently we have a new version of protocols under development in UCX, which would account this, which would take into account memory type. And once it is implemented, we will not need such a complicated scheme anymore. And actually, I think this is most important optimizations we did. So I think I'm done.
Okay, I'll continue with the rest part. So there are some optimizations we did in the upper layer as well. So for the first one, it's similar to what Mikhail said previously regarding, the topology and the NIC affinity. So we have machines that in practice do not have very balanced NIC affinity. For instance, we have instance with 8 V100 GPUs, but only with one NIC with 100 gigabits per second bandwidth, and this is close to one of the PCIe switch, which is shared with some of the GPUs. So for this case, we would turn on send GPU memory directly if the GPU is close to the NIC, and for the rest of the GPUs, they would have a CPU staging buffer to send it out. Apart from this, we also have some logics to in BytePS in general, just to use the shared memory if the sender and receiver are on the same node. We initially tried UCX shared memory transport, but we didn't find it as fast as we expected, so we had some workaround. Apart from that, there are two other points regarding concurrent primitives and also asynchronous support. So we looked at some existing options, for instance, Nickel, but we found that Nickel does not support concurrent calls. For instance, if we have an all reduce on one stream and auto on another stream, it may block itself in-house. But for ByteCCL, it's not an issue. So it can have multiple operations happening concurrently, because underlying PS Lite and UCF layer is thread safe, and it can process all these communication calls concurrently. The other point is it's more asynchronous in the sense that we compared it with Harvard, where in Harvard there's always some negotiation before any MPI calls can be invoked. So it requires some coordination between all the workers so that, if one of the workers is not ready for all-to-all, it will not really start the MPI call. But in ByteCCL, it's not, there's no explicit synchronization needed when we do an all-to-all. And we, track all these asynchronous requests and callbacks by the UCF callbacks. So if one worker started early, is faster than other workers, it can start the auto call earlier by sending it to its peers if the peer has already allocated the memory. Okay. So next slide has some performance results. Okay. We have some preliminary numbers for two models. We train on either one of them is on CPU, the other is on GPU. For the CPU model, it's around 1 terabytes of memory, and we train it on a CPU cluster with 4 nodes, and each one is equipped with 200 bits per second NIC. And we compare with the Harvard plus HPCX, and we saw around 12% end-to-end speed up of training this model. We didn't do very, detailed micro benchmark on the auto and all reduce primitives. We only, benchmarked it with, the message size we care about. But with the micro benchmark, it's kind of slightly faster or similar to what Harvard offers. On the GPU side, we also tested with a 16-node GPU cluster, each with overall 800 gigabits per second networking bandwidth, and each one has 8 A100 GPUs. The model size is slightly larger, and we compared with a nickel op in TensorFlow, and we saw around 8.6% throughput increase. And on this model, we also did some micro benchmark on the auto throughput, and it is on par with nickel. And I think nickel is very strong baseline, and we're actually very. I think the 8.6 speed up is already pretty good. This is the final part. So there's some pain points around UCX when we tried it and benchmarked it. For instance, some problems arise when we benchmark the internal performance. Some of the CPU to CPU transfer is not as fast as we expected, and the CPU to GPU transfer is actually very slow. There are some other pain points, such as some confusion on the prefix support on the configuration. For instance, some of the UCX environment variable does not support prefix, and it's not very clear to the user which ones are supported. And finally, there's some future work we're thinking about. For instance, for some of the systems we have internally and also in the community, the machine runs more than one microservice, and there's some non-UCX traffic that's occupying some of the NIC bandwidth. So with UCX multi-rail, it's always split evenly if it has multiple rails, if the NIC are of the same bandwidth, but it doesn't know, some of the NIC are already busy with some of the some other workload. So there's some space for workload balancing for this scenario. And also, of course, BiCCL is not fully open source yet. It's built on top of IPS, and we're looking at cleaning up the code and making it fully open source. And yeah, this is the final slide. Many thanks for many supporters from NVIDIA and Menlogs, and big thanks for them. And we can take questions now.
Hi, Ben. Thank you very much for presenting this. Any questions from people online? If not,
I just have a quick question about handling multiple UCP contexts for multiple GPUs.
Yep.
Yeah, I was just wondering how then this affects the number of endpoints that you create, and how the endpoints are created when you have multiple UCP contexts. Like, do you create one endpoint from every worker of every context to every worker of every other context?
Yes.
On every other node?
Yes, currently it works like this. We establish connections in auto fashion.
Okay, and how's the scalability of that? Does it really have any significant impact on resource usage?
The priority was the performance here, because scalability was not really pain point. And yes, it's not really efficient in terms of resources consumption. And as I mentioned, this is an intermediate step going to protocols version 2 in UCX, which is not ready yet. But yes, it's quite resource consuming solution.
Well, I'm actually asking more because I'm actually implementing something similar. So I was wondering if that's how you do it. And do you establish the endpoints eagerly at initialization time and connect all the contexts together, or is it like established on demand using client server?
We establish it in the very beginning, but that's how PS Lite works. Because Haibin, please correct me if I'm wrong somewhere, but PS Lite has 3 communication entities like scheduler, worker, and server. And in the very beginning of the program, all these processes are starting up, and scheduler establishes connections with all servers and workers, and servers and workers establish connections between each other. And it's done on the initialization phase. So it's not dynamically connected. It's connected statically at startup.
All right. So you already have all the connections.
Yes.
Great.
But it would not be difficult. I mean, it's not really a problem to implement dynamic connection in such a scheme. It just doesn't fit the API of PS Lite, of the way it's being used by the applications.
I see. Right. All right. Thank you.
Any more questions online? If not, I have one question. Is Michael, probably for you? Did you figure out why shared memory doesn't perform well? Because we kind of have been optimizing shared memory CPU to CPU specifically for a while now.
Yes, we're analyzing that together with other team members, with Marina and Dmitry from our team. And actually, I think the main issue we're talking about is that UCX comparing to RDMA WAN doesn't perform well on shared memory, because RDMA WAN, it's called RDMA, but actually it has IPC capabilities inside as well. So it utilizes IPC shared memory, but it starts four threads for shared memory transfers. And that makes, and in UCX, the best performance we get is we can achieve is using XPMEM, but we have to do some additional changes to enable it. There are some complications related to client-server communication model, etc. But that's not the biggest effort. The much bigger effort would be required to implement several threads for copying the data.
So they have multiple cores essentially pushing the data. Do you know if it's copying out in their implementation, or is also some sort of zero copy?
If I'm not mistaken, it should be copy out. Haibin, do you
it's
remember?
Not zero copy. It's not. Yeah, it's copying in and out.
I see. So it's just multi-threading.
Yes.
Okay.
And also, we had some different issues with GPU to CPU memory inside the host, but there are a lot of topological things to discuss here. So it's hard to answer because we had a bunch of issues with different root causes.
Got it. Let me introduce the next speaker. I hear a bit echo, and I think it's coming from me now. Let me fix the echo. Should be fine now. Okay. Our next speaker is Ethan Host from Microsoft. He will talk about usage and application of UCX in Azure Cloud. Ethan, floor is yours. We cannot hear you. Please unmute yourself.
Thank you, Pasha.
Good now, I can hear.
Yeah, perfect, thanks. Thank you, thanks, Pasha, and welcome everyone to this session. So I'm Jitin from Microsoft. So I lead the performance optimization team at Azure HPC. So this session, like I have organized in a simple manner, like we can go over a quick overview of the of Azure HPC. We can go a high-level overview of the two different representative SKUs, HPv3 and NDV4, two of the latest VM type. And since all of us are passionate about network, I would like to list out the different network features that are offered and on the clusters, and specifically on the Azure HPC VM images, like how we can quickly deploy a VM and then make use of middleware such as UCX and ready for communication. Some performance highlights. I'd like to show some benchmark results on HPv3, NDV4, and some scaling results, and conclude with that. Azure, as most of you know, like it's a really global infrastructure. We have like data centers typically like almost all around the globe. And different edge clusters also. So truly a global infrastructure. The main advantage is that you can have data reside close to your compute and close to your clusters. and you have service availability and like with competitive pricing. I don't want to go too much into the detail, but the main idea is that like you have different types of VMs for different class of applications. But in this session, I would like to focus on the HPC/AI VM types. So broadly, we can classify it into H and N, where H is the standard HPC applications where you have high compute and high memory plus high-speed network, which is InfiniBand. Azure is the only public cloud that offers IB on cloud. So that's the H series. And example HPC SKUs are HB, HC, HPV2, and HPV3. We'll go into HPV3 in some more detail in the following slides. And on the N series, it's basically the VMs with accelerators. So it can be, broadly, it can be classified into two again. The visualization SKUs, which is the NV series, where your typical workload is just maybe a single node, etc. And the deep learning or AI SKUs or even HPC SKUs, right? So that's the NC or NB series where we have accelerator plus high-speed network, right? So that's the NC and NB. And quickly, to identify, say, if a VM type supports IB or RDMA, is that so if the VM name has a little R, so that means it has RDMA support. And in all the IB-enabled VMs, we only have one VM per host. So you're not sharing, your VM is solely allocated to you. You're not sharing the host between some other customer, right? So that's a key. And also IB is exposed to the VMs using SROV, so complete host bypass, and you'll get the full feature support, right? And also you have P-key or partition key based isolation, where in the same cluster, there might be multiple customers running, but any allocation from a single customer using a single availability set or a VMSS, like those are terms where we use to group a set of VMs. So those VMs will always all have the same P-key, and they'll all be able to communicate only between that particular group and not to outside. So that's how we ensure isolation in terms of network. Let me go a little bit deep on the two representative SKUs, HPV3, which is an H series, and NDV4, which is a deep learning SKU, right? Two of the latest ones. HPV3, so this is how we design it. So, I mean, the main design goal is to like minimize any jitter from the host and or any jitter from any agents which are running on the host or the guest, right? So here, I mean, this queue is actually based on the Milan-X. Milan-X, as many of you know, like it was announced earlier this month. And on the same day, we have the preview clusters ready for customer access. So this is how we design it. So we have, again, this is configured in NPS equal to 2 configuration, that is NUMAs per socket, that's 2. Even in the same NUMA node, like we take out a certain number of cores for the hypervisor. 2 from here, this NUMA node, 2 from here, and 2 from the rest of the 2, right? So total 8 cores set back for hypervisor. So when the host boots up, it will see only these 8 cores. So any the Windows OS or any agents which are running on the host, it will always be using only these 8 cores. And the rest of the cores are all available to the VM. So that way, and the VM cores cannot land on the dedicated host cores. So we configure this using something called WinRoot, which is a Hyper-V feature. So that way we can ensure that there is no jitter whatsoever from host or from the VM activity not impacting host also, right? So both ways we ensure isolation. This queue has a CX6 NIC, And we offer these in different configuration. So we can offer all 120 cores, or if you want to pick, say, certain cores from each CCD, right? So 6 per CCD, that is 96, etc. And say for 1 per CCD, that's 16 core VM. So that's mainly to help with, say, certain applications that have the, say, licensing constraints, etc. So which is based on core count. So this way we can ensure you get the best performance, and at the same time, I mean, you're not overpaying for the license cost, etc. And one of the cool things here is that it has L3 cache of about 1.5 GB. I mean, it is almost 3x as compared to the previous version of HPV3, which is Milan. And you will see the benefit of the L3 cache coming to picture in the scaling graph. So I'll have some data towards the end of the session to show that. So that's Milan X HPV3. The other one is NDV4. So this is one of the most latest deep learning SKUs that we have. Again, I mean, similar design ideology. So here also we take out a certain number of cores per each NUMA. So 8 cores per NUMA, so 32 cores are taken out in this case, and the rest 96 are given to the VM. So interestingly, like, so this queue has 8 A100 GPUs and 8 CX6 200 gigabits per second IB mix. So it's a massively powerful machine, yeah, I'll show some results towards the end. And this has made up into the top 500 in this list, so top 10 ranking. So we'll show that later. So basically, that's these two representative SKUs. I just wanted to give a highlight of how we define the SKUs and how I mean, we ensure that there is no jitter from host or no jitter from other VMs, etc. Right? Some of the network features that are available on Azure. For example, I mean, we have different types of SKUs, right? So CX5 based older generation SKUs, and the newer ones have CX6, 100 gigabits per second, and then 200 gigabits per second, right? And all the different features that we are very much familiar on the bare metal side, like DCT for the scalable transport, hardware offload, I mean, both for collective offload and also hardware tag matching. UD-based MCAST, SHARP. I mean, I'll have some SHARP results later. Dynamic routing, advanced congestion control or adaptive routing, and also better reliability with Shield, right? So, I mean, all these features are exposed, I mean, to the VM. What is not exposed is, say, we don't expose the QP0 for because of security restrictions. So, I mean, the VMs may not have available, I mean, provision to run, say, IB DagNet or IB NetDiscover from the VM. But I mean, you can always get that using special tools, etc. Right? So that's not a limitation, but I'm just giving the full picture. Yeah, so since we covered the different network features, I just wanted to quickly share some of the results also, right? So GPU direct RDMA, and I don't have to explain this feature because I mean, all of you know this. So I mean, basically it provides a direct DMA path between the different GPUs on internode, right, or network, right? So on this graph, I mean, on this slide, I have shown like two different screenshots. One for the RDMA host memory, like all eight IBs doing IB bandwidth, and each of them getting the peak close to the 200 gigabits per second peak bandwidth. And at the same time, so this is for GPU direct RDMA. In this case, at this time, it's all simultaneously doing the GPU direct RDMA transfer. And you can see all of them again reaching close to the peak performance, right? Peak bandwidth. So collectively, this queue can like push out around 1.6 terabits per second at the same time, right? So And it's and since we export, export the IB over SRIOB, it supports all. Complete support for verbs, or so that any GDR capable MPI or libraries can make use of it, right? The next one is Sharp. Sharp is currently not enabled on all the clusters, mainly because Sharp resources are constrained today for the HDR switches, right? But that's something that NVIDIA is addressing in the next generation. But so currently we have enabled Sharp only on dedicated NDV4 clusters. NVIDIA team has done like several optimizations to enable Sharp on cloud environment. So one of the cool things is UCX-based Sharp AM or Sharp D communication, because now you can get the PKey-based isolation for this communication rather than going over TCP/IP. Optimized Sharp tree initialization, which really enables you to like scale out to really large scale. And also connection keep alive, so that you can reduce the traffic to the UFM or the Sharp AM in this case, right? And also GRH support, like so that again, if you want to like really scale out, to support that. So in the graph, I have shown two lines here. One is with Sharp and without Sharp. So you can see we are hitting around 227 or 220 gigabytes per second. Without Sharp, it's about 189 gigabytes per second. So again, this is very much close to the peak performance here. So 200 gigabits per second NIC, and all of them, theoretical peak is around 200 gigabits per second. So we are reaching around 190. And then with Sharp now, we can see it is now limited by the the NVLink performance. So about 227 gigabytes per second, again close to the theoretical peak. Congestion control. We'll have some detail or results. Especially with the application results coming in on Wednesday's session. In the cloud native supercomputing performance isolation. So here I have captured GPCnet results for say 512 VMs all running at the same time, right? A group of them doing creating artificial noise, and other ones doing the benchmark. Two configuration: one is CC disabled and one CC enabled. And for the three different benchmarks, the latency, bandwidth, and all reduced, right? So you can see, and the graph is actually plotting the congestion factor. Ideally, it should be 1. Basically, ideally it should be around the 1 mark, right? So we can see without CC, it's all around the mark, right? And then with CC, it's very much to the ideal performance. So same story here with the bandwidth and also the all reduced. So we can see, and this is really important in case of public cloud, because we have multiple customers running their workloads at the same time. Even maybe on a supercomputer, you can like traditional supercomputer, you can just do a check your queue and see what other customers are running, etc. But cloud, you cannot see what other customers are running, etc. Right? So congestion control really enables you get the best performance on consistently in this case, right? So so we are still in the experimentation phase. We haven't enabled it all across, but our plan is to enable congestion control on the fleet wide, very soon. And the other one is adaptive routing. So this is again a quick illustration of how adaptive routing can help here. This is an this is very interesting actually. So this we saw a big performance dip even on a 4-node job with say static routing. And then we mapped out the actual the routing paths that it takes, and then we found out okay, this one particular link was used for the 2 different communication paths, right? So let me go into a little bit deep here. So this is a logical ring, like 4 ranks A, B, C, D, so 2 ranks on same rack. So these are 2 different nodes, and 1 node here and 1 node here, right? And we have IB0 switches, which is the leaf switch, and then IB1 switch, which is the higher level switch. So, I mean, if we do the static routing, right? Say, for example, destination-based routing. So A, if it wants to talk to B, it will go to IB13 because it's in index 3 in this rack. So it will go here, and then 1A and 1B. Similarly, B, when it wants to talk to C, it will go to IB6 because it's in 6th position, and then here and then here. So 2A, 2B, similarly 3A and 3B, and 4A and 4B. So you can see 1A and 1A and 3A uses the same link and the same direction. So and we even when we measured the point-to-point performance for each of these, we saw okay, this particular one was cut into 2. And with adaptive routing enabled, right, that effect is gone. So again, the nickel bandwidth results itself, but so here we can see adaptive routing disabled. We can see the peak bandwidth was cut into 2, like here, and then with adaptive routing, you can see it was reaching close to the peak again, right? So so it is enabled by default on the NDV4 and not on the HPV2 or HPV3 SKUs, because certain MPIs doesn't really work really well with adaptive routing. But you can always choose a different SL where adaptive routing is enabled and use that. So we have more details on adaptive routing and how it is configured for the different SKUs in this particular link. And finally, a quick note about the HPC VM images. So, we have the different networking features, technologies, etc. But how you can make use of it in the cloud, right? So one can easily like deploy a VM like based on the HPC VM images. So we have 2 flavors. The CentOS-based HPC VM image and the Ubuntu-based HPC and AI VM image. So both these images, we have all the different or mostly or widely used software packages. And it also comes with the recommended optimization configurations, everything. So the main idea is that like, one can deploy a VM easily and then get out-of-the-box performance. It has also the different MPI libraries, HPCX, Intel MPI, MapReduce to OpenMPI, and also UCX. So UCX, let me make a quick note here. So UCX is I would say the most widely used or widely recommended transport layer for Azure, mainly because it gets you the best out of the box performance, and it's very stable also. Like for HPCX, again, it uses UCX, Intel MPI, again UCX, and OpenMPI also UCX. So we really recommend UCX for our clusters for this performance, etc. And some of the results I show now here, and also the different benchmarking stuff that we do are mostly using HPCX / UCX. So quickly, looks like not much time left, but so HPV3 MPI performance characteristics. So again, like I mentioned the SKU and how the NICs are exposed. So I plotted the MPI micro benchmarks, noisy latency, bandwidth, and bidirectional bandwidth. So we can see that it is getting 1.5 microsecond the MPI point-to-point latency. And like, for other public clouds, this is probably almost 10x higher. But yeah, we are getting about 1.5 microseconds. And again, the bandwidth, again, close to peak, 24.6 gigabytes per second, same with bidirectional bandwidth. So it kind of illustrates that there is no overhead from the host layer. So, anything that you get at the bare metal, like we can again get here. And this is again the same thing for NDV4, but this time our GPU direct, device to device, right? GPU to GPU, again, like two different nodes. So again, MPI latency of D2D of about 2.43 microseconds. Again, the GPU direct RDMA OSC bandwidth, again, close to peak here, and also same here for the bidirectional bandwidth. And finally, yeah, this is a very, very interesting slide, I would say. So these are some scaling efficiency graphs for three different applications. Like, again, Fluent for the different two different models and OpenFOAM. Really commercial applications, right? So, so we scaled it from 2 VMs to all the way to 128 VMs, etc. Again, these are running on Linux. So, like I mentioned, it has the larger cache. And again, the MPI used is HPCX, which is over UCX, right? So, interestingly, like, look at the scaling efficiency, like it goes super linear after some point. Again, the same trend for the three different applications. So the larger cache, it comes in the picture after some time and after the scaling to some level, and then you get really nice speed up. More details are mentioned about the configuration, the PPN, the software stack, etc., are provided in this particular blog. With that, let me conclude. So it is pretty obvious that supercomputer on cloud is real. Azure HPC Cloud has made into the top 500 and top Graph 500 top rankings. Like I was referring earlier, like NDV4 made it into rank 10 in the top 500 earlier this month. And again, rank 17 for Graph 500 using HPV2 last year. The best part is that cloud kind of makes it available for everyone, right? So that's, previously it was, supercomputers were available for maybe national labs or certain universities, etc. But now anyone can access supercomputer, and HPC middleware such as UCX really enable the cutting-edge technology and then get high performance and scalability. With that, let me conclude and have some pointers about getting started, the different VM images that we discussed, how we can quickly deploy the VMs, HPC VM series, GPU VM series, and some performance blogs here. With that, let me conclude, and I can take any questions.
Ethan, thank you very much for presenting some really impressive numbers, like 1.5 microsecond latency in the cloud. That's what you see typically in homegrown supercomputers. Any questions for it? Sorry.
I really wanted to thank the NVIDIA team also for the close collaboration and like making things much better. NVIDIA UCX team, especially like Devendra, Josh, everyone really, yeah.
Sure. Any questions from online for Ethan? If not, I have one question. So, sure. in terms of UCX, what do you think? What features we are missing? What we should work on in terms of cloud deployments of UCX?
I think we have a few, I guess, right? So one of the things, I would say, we had, I think we have a list finally, but one of the things that quickly comes into my mind is Spark, right? So, we had some time back tried to use Spark on UCX and getting into some issues, but that's really something. And then one of the other things is that shared, like intranode communication. There are still some issues, I would say. Like depending on what kind of kernel features are available, etc. So that is one thing. And then may not be really a UCX issue, but I would say like we are seeing some kind of some rare issues with DCT as well when we try to scale up. Maybe that's a firmware issue, but those are the different minor things.
Thank you. Yeah, it seems like we hear shared memory more and more, so it seems like we have some work to do to nail performance there. Any more questions? If not, thank you very much, Ethan, again for the presentation. Really cool stuff.
Sure.
Our
Thanks.
next presenter is Kendra Finati from Argonne National Laboratory. He will talk about MPH and UCX. Ken, you should be able to take over the presentation and share the slides.
Okay, let's see.
We can see it and we can hear it.
All right, sounds good. Okay, thanks, Pasha. So yes, my name is Ken Raffinetti. I am a software developer here at Argonne National Laboratory, and I'm going to talk about kind of the state of the union of MPICH and UCX. So the way we use UCX in the MPI-CH or MPICH project. So just a little background on MPI-CH. You know, we're very HPC oriented. You know, we aim to be, you know, the MPI used on lots of large scale clusters. And the way we do that is we kind of develop MPICH here at Argonne, the core open source version of MPICH. And then we rely on many of our partners to kind of pick up the open source version that we produce, extend it, tune it, package it for their specific use cases, their hardware, their software environments, and then you know, then the outer ring here is the applications that sit on top of those derived implementation. So that's kind of the MPICH development and distribution model. So today I'm going to talk about how we're using UCX and MPICH. So we've been using it for quite a while, dating back to, you know, an initial integration. I don't know how many years ago, probably, you know, around the time of the first annual meeting. And then I'll hit on a couple of specific points. You know, there's you know, things that keep coming up with request handling in MPICH that's different than the way requests, MPI requests are handled in OpenMPI, and so how that kind of affects us, and how UCX can support us, which today is much better than it was. How we're using the UCP Active Message API, this optimization we're using for multi-threading called multi-VCI, which I'll explain more later on, and then some things we have slated for work in the future, and a few other odds and ends before we wrap up. So that's what I'll cover here. So again, more background on MPICH. So MPICH, this is kind of a simplified diagram of its structure. So the important thing here is now we're using what we call CH4 as a default device layer implementation. So the CH in MPI-CH stands for Chameleon, which was a project that dates back, you know, prior to MPI, so over 30 years or so. So Chameleon has evolved over the years. This is the fourth iteration, which started probably about 7 or 8 years ago, maybe a little bit longer. It was kind of a redesign for lower overhead, kind of more capable network APIs like UCX, like libfabric. So you can see UCX kind of sits below the CH4 layer as what we call a net mod or a network module. And essentially UCX, the goal is, the MPI API calls directly down to UCX without doing hardly anything at all. We try to minimize branches, minimize interpretation of arguments until we get to that network module where, in terms of UCX, it can handle a large portion of the MPI API, quote unquote, natively. And so there's a pretty good match between APIs there. And that, so when we call UCX directly using, using what we can from the MPI API. If there is a bad match, if the call is complex or uses some, however you want to, however complex it gets in MPI, which it can, then we call up into what we call the generic layer. And the generic layer is basically the MPitch protocol layer where we have a packet, packet header and packet handlers. And this is what we actually use the UCP active message API for kind of layering that MPitch protocol over the available UCX transports. So this is the state of support today. So again, we developed the UCX netmod. Primarily, the Argonne MPitch team maintains it at the moment, though we have help from the NVIDIA Mellanox team and had a lot of help in the past on that. So we just released a beta of MPI MPitch 4.0. And so MPitch 4.0 now adds all of the new MPI 4.0 functionality that was just standardized earlier this year. This includes like large count APIs, partition communication, persistent collectives. So all that is there now in MPI-CH. It's in beta status right now. There's still some bug fixes that need to be applied, but we're hoping to have an RC and a full release out, hopefully end of the year. If not, then very early in 2022. So we have included an embedded UCX 1.11.2 in MPitch. So if you are building from source and you select UCX as your configuration and you don't have it installed on your machine, it will build the embedded version. We switched configuration. I think other projects are doing this too. We now prefer the external library if it can be found on the machine. Again, if it's new enough to support some of the features that we require. So I'll talk about some of the changes we made and how we now require newer versions of UCX in order to support them. This version of MPitch has also done a lot in terms of GPU support. So MPitch supports 3 flavors of GPU: NVIDIA, AMD, and Intel GPUs. Though for UCX, we only support the NVIDIA and AMD configurations. So, and we have tested with that. We have clusters in-house or machines in-house where we've ran and validated these configurations. So in terms of what's natively supported by UCX in MPitch, again, like I said, so point-to-point is obviously a good match for the tagged interfaces. We've recently upgraded to using the NBX versions of the tagged interfaces, which I'll talk about later. We have contiguous put-get RMA support, depending on your window flavor. So we support this for WinCreate and WinAllocate windows in MPI RMA. We don't yet have it merged. We want to merge atomic support. It was under development by one of my colleagues here at Argonne who unfortunately left for a different position. So that still needs to be kind of worked on and merged into the MPitch main branch. But there is a PR, and I think some of the concerns were mainly around UCX versions, which I think we've resolved now, so that we might be able to speed up the process of including that fairly soon. Like I said, the generic path, we're now using the CH4 active message, the UCX or UCP active message API, which is a pretty straightforward port. I'll talk about that in a later slide. Something we don't support with UCX is MPI dynamic processes. So it's the support for things like MPI com spawn and connect accept and things like that. We actually have a pull request that looks to add this, though we're running into an issue we had in the past with the size of the worker address. I see that there's a pull request from Mikhail that's looking to address, shrink the size of the worker address. We haven't tested this yet, but it's something I've marked as potential for helping us through this issue. Otherwise, it's probably a PMI. It's a PMI limitation that we could probably work around. We worked around it for address exchange, business card exchange during MPI init. I suppose we can implement a similar workaround for dynamic processes. It would just be nice if we didn't have to. And then I have this box here, just some raw performance numbers. I ran these a while ago, but they still hold fairly true today. Just illustrating that we get nice latency and bandwidth performance kind of out of the box with UCX. It doesn't take a lot of effort to realize how the good performance numbers that are possible using MPitch with UCX. So again, we get good latency and bandwidth. I think this is using the RC transport. This is 2 nodes, 2 InfiniBand nodes in our JLSE system evaluation cluster, one of our evaluation clusters here at Argonne. Let's see. Okay, request handling. So this comes up. This has come up in the past, and it's something that continues to come up. In the integration of UCX and MPitch. So just as background, so MPitch, unlike say OpenMPI, allocates objects from its own internal object pools, and it assigns them C integer handle values, or assigns integer handle values, whether it's C or Fortran. But literally, we have this typedef int MPI request. So I think other, OpenMPI and maybe other communication libraries use pointers for handles. We use integers, and so this is this complicates things a little bit. But it does have some benefits. So you can encode information in handles like this. That's kind of why we like it. So it's eliminates maybe a memory lookup for certain types of objects in MPitch, not necessarily requests, but other things like data types. So it's kind of a nice feature. But the other reason it's likely to stick around is that it's part of our ABI, and we're really ABI sensitive in the MPitch project. So we're unlikely to change this anytime soon. So it was clear that the tagged APIs in the past were not necessarily designed around this mode where the communication library is going to be allocating its own request objects. But the MBX interfaces are a huge improvement on the past APIs. Less so for send. So I think I talked about this last time I gave an update. So for tag send MBX, we're still not providing our own requests to the UCX library. I think as one potential solution for this would be to use the MPitch request as the UCX request. We're not doing that because we really like the optimization where UCX doesn't allocate a request at all, because MPitch doesn't have to request or allocate a request at all, and that's a nice optimization for small kind of immediately complete operations. As I noted before, I think I suggested, well, what if we add a flag that tells UCX, always return if you can't immediately complete this operation, and then I'll know I'll allocate a request and I'll give you the request and you can use that. This turned out to not work as well as I thought it might in my head when I suggested it. The reason was, I try the operation, it doesn't immediately complete. I allocate my request and then I try again, and the operation does immediately complete. So it was kind of like a it didn't necessarily work as well because I think I was the code I was writing was expecting the second try not to complete immediately, but then it did, and so it ended up kind of making that code really messy to handle that situation. So anyway, on the send side, things remain mostly the same with the adoption of NBX, which is actually not that big of a deal. It was really the receive side that was mostly problematic, and again. We're not using the ability to provide the request to UCX as maybe we thought we would when we originally looked at these APIs. The major improvement in the NBX interfaces for tag receive is the addition of the user data parameter, because that we just use as a pointer to the mpitch request struct, the underlying struct, not the handle value. And so what this gave us was a way to make the mpitch request available in the completion callback no matter what. Because before we didn't have a way to do that, because the UCX request had, may not have been allocated yet when, because the UCX completion callback might have executed before we had the chance to associate the UCP request with the mpitch request. Then we had to have all this complex handling. Now, because we have that user data parameter that's present in the start of the receive call, then we always have access to the mpitch request at completion time, which significantly simplifies the request handling. So that's really great, and we're happy about that. Active messages, like I said, so now before we used to layer the mpitch generic active messages over the tagged interfaces. But this had some negative performance implications because we were always checking to see if there were generic messages in the queue or in the receive lists. So now we're using the active messages, which kind of are decoupled from the tag receive queues, which eliminates any kind of overhead by having both sharing the same resource. We're still using the NB, so we haven't yet updated to the NBX active message interface. So we're still using the old NB interface, using the whole message flag. It's good. The porting was really straightforward. Eliminated that message matching overhead, like I talked about. We do need to copy data for alignment purposes, but again, I saw a PR from Mikhail that may have addressed this for us that we should probably test, but it looks like we can now specify an alignment for incoming active messages. We do want to update to NBX, the NBX version of the interfaces, but we need to do some more testing. I think the answer to this question is yes. Does the active message interface support device buffers? But I think we had run into issues in our testing where we saw problems with that. So I think we've seen some fixes come across that may have addressed that. But anyway, that's something that we need to do some more testing on and see if we can upgrade to the newest version of the interface. I'll talk a little bit about multi-threading optimizations we've done inside MPI-CH. So we have what we call a virtual communication interface, or VCI, that is a kind of an object, a software object inside MPI-CH. The idea here is we allocate these VCIs and map them to network resources. In the case of UCX, that's a worker. In our implementation, and then threads can use these independent resources in a more scalable fashion rather than trying to share resources and contending for locks and things like that when using them for multiple threads. So there's I put the title of the paper here. And I think Rohit's even on the line, so he could tell you more about it. But this is based on work from a student of ours. Well, he was a student at the time, about how to improve MPI thread performance without going as far as having a thread specific interface for MPI, but using the existing MPI 3.1 interfaces. And this, like I said, mapping thread operations to independent resources in order to get good scalability. So this is kind of the nuts and bolts. We still use a single context, but we do indicate that it's going to be shared by threads using different workers. And then our workers, like I said, MPICH is locking the workers by protecting the workers so that operations are serialized. There will be multiple threads potentially using different workers, but they'll only be using them one thread at a time. So we use the serialized thread mode. And then we do an all-to-all address exchange endpoint creation so every depending on how many workers you have, if you have 2 workers, then you have twice the amount of addresses, endpoint addresses stored. So it is a big resource hog, as we talked about in one of the other talks touched on, though in the context with context rather than workers. And so I did some performance evaluations of this actually last night, yesterday, using a couple available multi-threaded benchmarks just to show how this is working fairly well. This is using Artem's multi-threaded communication benchmark. This is point-to-point message rate test with MPI. This is on Intel Xeon platform here, Skylake with ConnectX-6, 1 process per node. Importantly, we're using COM per thread. So this is how MPICH distributes, communication to the different VCIs internally. By default, it uses different communicators or different windows for RMA, like I'll show later. We also have, planned schemes for distributing work based on, the user, the tag of the message, or potentially the rank. Those are things we want to look at adding. But right now, using a thread per communicator, or communicator per thread is the default way to get kind of isolation amongst threads. So you can see this is pretty good scalability, especially for small messages. You see, almost linear increase as you go to 2 threads and 4 threads here in the message rate test. Similarly with RMA, and this is log scale, so be careful how you read these. But again, this is a latency graph. So we see with small messages, the latency, there's virtually no overhead as you increase the number of threads. Again, we're using this -W option. So this is the LANL RMA multi-threaded performance benchmark. We're doing a window per thread here. So again, we have to isolate threads in some way to kind of make sure they're not contending for resources. But virtually no overhead and small message latency. And in bandwidth, again, we're getting fairly linear scaling as we increase the number of threads. What we're looking at working on in the future. So right now, as I said, we have support for contiguous RMA put get with MPI, with MPI RMA windows. One thing that we should add, we have it for our libfabric integration, but we don't yet have it for UCX, is support for non-contiguous RMA. And this is, I'm not saying, the UCX doesn't support non-contiguous data types, but what I mean is when we have, a dense data type, then we can, instead of calling up to the generic layer and packing all the data into a buffer and going over the emulation path, we could still use native operations. We just issue multiple per contiguous segment of the dense data. If the data is sparse, then we'll just pack it and again issue a native operation as opposed to what we do today, which is fall back to the generic, the active message based or layered implementation, which is not as performant. Again, I talked about we need the dynamic process management to have a full MPI implementation with MPICH UCX. So we need to test that new address format or implement a workaround for when we can't support it. Native atomics, again, I talked about that, so I won't say anything again. And then what's down here at the bottom, and it's something that we also definitely want to look at as UCX collectives. Prototype this out, evaluate it, assume, we've heard a lot of good things, so we want to get that integrated, and hopefully it's pretty straightforward porting from what we have currently, which is the HCall integration in MPitch. Other odds and ends. So I put this up here last time. I think I talked at the annual meeting, but I'd be a little more specific about it now. So we run a lot of testing. We do a lot of Jenkins testing with our MPitch UCX integration, both nightly and per pull request. One thing that's been really great for us is the addition of sanitizers into the Jenkins tests. So we are using address sanitizer with MPitch plus UCX, as long as we set these environment variables in order to disable some of the memory hooks that UCX uses by default. Just as a point of note, that address sanitizer does work well with UCX as long as you disable those hooks, which has helped us find leaks and other weird behaviors. We also use undefined behavior sanitizer, which has been great especially for initially discovering that alignment issue with active messages, because as most folks know, on Intel platforms, alignment is not strictly enforced. You can do pretty much anything you want. It just won't, it may not perform very well, but if you are to move to another platform like ARM or Power or something like that, you might get a SIG bus or something and a crash. But luckily, undefined, the UBSAN can find this stuff for you no matter where you're running. And so you can implement a fix for it before you get surprised by a crash on a different system. So that's all I've got. A list of pointers here are the MPitch website, mailing lists, our GitHub, where we do all of the MPitch development out in the open. So if you have an issue or you want to fix something, please submit an issue or a PR to us. We'll be happy to take a look. And we also have a Slack channel where we discuss MPitch. There's some NVIDIA Mellanox folks on there already, and we're happy to have more there. Just ping me for an invite. So that's all I've got. Thanks. Some questions? I see one in the chat from Yossi about with the immediate completion. Maybe we're not setting no immediate completion for the second. That's a good point. Yeah, I guess we haven't tried that. I could see if that gives us any benefit. I guess I'm at the reason we're not doing it is I think at that point we've already resigned ourselves to allocating the request, and so we might as well just go through the full completion path. But it's worth a shot. We could see if it does provide any benefit.
Any more questions for Ken?
I was wondering, what was the exact problem with trying with forcing immediate completion first, and then second time without it? And if it at the second time it completes immediately, what would be the issue with that?
Yeah, I'd have to dig back in my notes for why that is an issue. Yeah, I guess so if I'm remembering correctly, so we essentially, we have this completion handling that either happens in the completion callback, or it happens after we know the operation is immediately completed, and whether or not we need to. I suppose if we just had a helper function that did that, then it'd be trivial to kind of do it in both places. Mm-hmm. So I think it boiled down to that. But yeah, like I said, I think because once the immediate completion has failed, and we're gonna, like at that point, we say we are gonna go ahead and allocate the request, and that's expensive. We're taking a lock, we're grabbing something out of the memory pool, we're initializing all the fields. At that point, we might as well just go through the full completion callback path. The immediate completion isn't really going to save, whatever it saves us is not going to be much, I think, over the request initialization at that point. So I think that's why we kind of resign ourselves. But yeah, it's probably not as much of an issue to do the completion processing in both places, whether you do it after immediate or in the callback. So I'm probably overstating the messiness there.
Right. So because of this, you right now do not use that immediate completion flag at all. You just always create the request.
No, we only create the. So we don't supply force immediate completion, but if the request immediately completes, right? So if we get back null from tag send NBX, then we just return the user a pre-completed request handle. Mm-hmm. If it fails, if we do get back a UCX request, then we go ahead and allocate the MPitch request and associate the two, because one of the things that's improved, at least over initially when we integrated UCX, that send no longer triggers a progress if it allocates a request. So we can confidently say that if we get back a request that it's incomplete, and we can associate the MPitch request with it before the completion callback.
Okay, because that's what I was wondering. So how can you make sure that the callback has not already been called before you do that association? Okay.
Yeah, and that change went in a long time ago, probably like 1.6 or something. Yeah.
I see. And is this also one of the reasons that you are not using field request and not passing the request to UCX? I mean, you pass MPitch request as the user data, right?
Yeah, we do that in the receive path. We do that in the receive path because we always have a request in the receive path, but in the send path, like I said, we can return this pre-completed request, like statically allocated pre-complete request, which again is a huge savings. It saves all that memory pool allocation and it field struct initialization. So that's why we don't supply anything to UCX, in the immediate, in case the operation can immediately complete, because it's a big optimization.
Yep. All right. Yep. Thank you.
Thanks.
I just have a short note that regarding the issues with active message alignment and device memory support, it should be already in place in the master or UCX 1.12. So it would be good if you can test it and raise an issue if something's not working still.
Sounds good. Yeah, we'll take a look at that.
Okay, thanks.
All right.
Any more questions? Okay. Let's see if we have any more questions. Ken, thank you very much for presenting this. Good stuff. Now we'll go for a break until 10:30 a.m. Pacific time. And please come back. We have next session, which is will be focusing on binding for UCX, UCX Julia, UCX Go, UCX Java. So please join us.